Hi, my name is Jessica, and I'm a current senior at the University of Massachusetts Amherst, and I study mechanical engineering. For my MassURC presentation, my research project is formally titled Characterization of Tantalum Cold Spray Coatings Using Atomic Force Microscopy, and this research is with the advisor, Professor Stephen Noneman from UMass Amherst. So to briefly go over what cold spray is a thermal coating process discovered in the 1980s, and it's a process in which feedstock powder material is accelerated through a compressed gas chamber at very high impact velocities onto a desired substrate. So these resulting solid-state coatings on these cold sprayed parts, they often display advancements in mechanical properties and are used in applications such as in the aerospace, energy, and defense industries. This minimizes costs on a manufacturing level for these industries and also maximizes efficiency of a project design and assembly process. For example, spray techniques can result in additively manufactured parts, and these solid-state coatings can be beneficial for quick repairs and viable alternatives to replacing entire parts that cannot afford long periods of project delay. Additionally, depending on the metal used as feedstock powder, manufactured parts can also be used for biomedical applications such as prosthetics and surgical instruments. So to go a bit into what the feedstock internal powder feed means. So feedstock powder can range from metals to metal matrix composites to ceramics, and these materials are deposited in their solid state onto substrates at temperatures without melting. So during the operation process, inert gases like helium and air, they're being preheated to temperature ranges from 0 to 800 degrees Celsius and then accelerated through a velocity nozzle chamber with the feedstock material. So this temperature range is just simply lower than the melting point of the feedstock coating material, thus gives the process its name of cold spray. Not to be confused, cold spray is actually not a cold process. It's actually one of very high temperatures. But since the temperature range is lower than the actual melting point of these metals or ceramics or metal matrix composites, we call it cold spray, even though it is part of the thermal spray coating process umbrella. So the material that I use in my research to spray as feedstock powder is tantalum, and a few general characteristics of tantalum. Tantalum is number 73 on the periodic table, and it is a refractory metal, which means it has high hardness and high melting point, which are great characteristics to have for a cold spray coating process. And it also displays corrosion resistance, which obviously will play a big part into the lifetime and durability of materials manufactured with tantalum. And also, tantalum, leading off of that, is unaffected by chemical corrosion under 150 degrees Celsius. So, cold spray tantalum can also eliminate post-repair heat treatments because this can be costly and time-consuming. And general applications of tantalum, there's a lot within the medical field, as I mentioned before. There's low toxicity of tantalum, and there's great osteointegration capability. And what that is the direct structural and functional connection between a living bone and a carrying implant. And then also tantalum demonstrates good radio density, which is opacity to a radio wave and X-ray portion of a electromagnetic spectrum. And then within military applications, tantalum is great for durable electronics capacitors, munitions, and also can extend the material life of parts upon cold spraying onto a substrate. So what happens when cold spray materials spray onto the substrate? For example, when tantalum gets sprayed onto a substrate such as aluminum or stainless steel. So when the cold spray material sprays onto a substrate, nanostructures and microstructures can formulate at these material substrate interfaces, and this is caused by plastic deformation and adiabatic shear instability. Plastic deformation causes hardening mechanisms at the interface, such as work and strain hardening, and then additionally, high levels of porosity can result from the interface characterization, and these oxides can have an adverse effect on the final product. So, depending on the porosity levels, this can be very harmful for the end product, or we need to look into what the presence of oxides actually mean. So, Current characterization techniques to see what happens at the structure interface of these microstructures. The SEM, LM, TM, they've been used to really analyze the microstructures at the surface interfaces between the material and substrate. And additional X-ray spectroscopy is used to see which materials and chemicals are at the deposition layer. However, these scanning techniques only provide the microstructure imaging. They don't tell further characterization such as deformation behavior and Young's modulus of the samples. And this all falls under mechanical properties and characterization. And so for my research, I am going to be using the AFM, atomic force microscopy, to understand the mechanical deformation characterization of these tantalum spray coat samples to see what happens at the material substrate interfaces. I can quantify this with Young's modulus and topography characterization. So the general gist of AFM is that it uses a cantilever beam and tip assembly that comes into contact with a sample. And this is a complete non-destructive a general non-destructive way of characterization because unlike an instrument machine where you can find the Young's modulus by pulling apart something and pulling apart a sample, characterizing what the Young's modulus is, the AFM, it does not destroy the sample. Rather, it uses the probe to repeatedly come into contact with the sample, and through feedback electronics, lasers, and photodiodes, they're able to characterize what the local modulus of elasticity is. So the actual method that I use for the AFM is called bimodal AM/FM tapping mode. And what this is shown in the schematic here. It's a fast force mapping mode within the AFM where two resonances are driven at the same time. The first is the higher resonance FM mode, and then the second is the first resonance AM mode. So the topography feedback is driven by amplitude A1 within the first resonance AM mode, and then an oscillation is maintained using a feedback loop. But then simultaneously, the higher resonance in FM mode is driven with A2 amplitude as seen in the figure, and then the phase and amplitude feedback loop maintain constant oscillation while the sample is being scanned. So as a result, we're getting two feedback results at the same time, topography and the Young's modulus. So to summarize, the first mode provides information on the topography, amplitude, and the loss tangent or phase, and the second mode info is about the stiffness or modulus from the frequency shift or energy dissipation, which also relates to the amplitude. So the first method that I looked at and sample that I looked at was a tantalum aluminum substrate material sample. And what I was looking at was the oxide layer on top of the aluminum from a top view perspective, so a bird's eye view. And as a result, I looked at the height topography as seen in the height retrace because it's crucial to confirm its smooth surface before analyzing the Young's modulus. And then on the right is the Young's modulus of the sample. And as you can see, it's very clear that this is a top view because you can see that the tantalum is sprayed on around like 170 gigapascals. And then the aluminum is the maroon color, which is around 70 gigapascals, which is the Young's modulus of aluminum. So these results show that the bimodal AM/FM tapping mode for the AFM can resolve local heterogeneities of two different metals on a deposited surface as seen through aluminum and tantalum, but it also demonstrates a great promise as nanocharacterization tool for refractory surfaces. A disadvantage is that because I scanned the results from a top view, this couldn't analyze the oxide layer of what happens underneath the tantalum because AFM is a surface technique. Instead of top view, the next step I took was to analyze the cross-section view, which gives a direct relation as to what happens at the tantalum substrate interface, because the cross-section is scanning exactly where the tantalum meets the stainless steel. In this case, the sample I looked at was stainless steel instead of aluminum. So similar as before, I looked at the height retrace of tantalum, stainless steel cross-section, and then the Young's modulus as well. And as you can see, the Young's modulus highest limit is around 60 gigapascals, which is significantly lower than the named gigapascal Young's modulus of tantalum, which is around 170. And the lower Young's modulus may be due to reasoning such as at the interface, it's super hard to find where the tantalum actually is. And then the difference in Young's modulus values between experimental and theoretical may also be due to the fact that the AFM measures reduced modulus and that may result in lower Young's modulus values. So, future work on this project would be to obtain better results on the tantalum substrate cross-section for the Young's modulus, and some factors that occur during testing that make it very difficult to verify if the scans are accurate or not is that there's maroon discolorization of results, the indentation depth of the tip. Oftentimes, it's higher than 10 nanometers when it should be less than zero point 0.4 nanometers. And we also want to eliminate the negative modulus values as well as abnormally low or high Young's modulus values. So, as seen before, there was around 60 gigapascals for the tantalum when it should be around 170. And really troubleshooting the AFM can improve our results this way. And additionally, it is possible to recut the cross-section samples and polish them for a smoother surface for AFM scanning, and this will eliminate the AFM struggling to find that surface that it can accurately scan the results. And not, thank you so much for listening.